Now let's talk about server memory and how it differs from desktop memory. Well, of course, it's still memory, so it's still volatile, high-speed, small storage for the system. And in fact, our servers can't live without it. They can't run unless they have a place to store the code and data needed to process. So just like in a desktop system, a server is going to need memory. So how are they different? Well, in the server, one of the big differences is going to be the amount of memory slots and channels, which we discussed in the CPU video. The quantity of memory is going to be increased because of the number of slots that we have, number of channels available, as well as the available DIMMs. In server memory, we have significantly larger data capacities per DIMM than we do in the desktop world. Currently in the desktop world, 32 gigabyte DIMMs are the largest readily available memory modules. However, in the server world, 128 gigabyte DIMMs are available and 256 gigabyte DIMMs are available in a limited capacity. So simply by the sheer density of storage per module, we can have more storage in a server environment than we can in a desktop. And this makes sense. Since we're often packing more processing power into a server, we want to also increase the memory resources so that the processing power can be taken full advantage of. Now, that does not mean that a server has to have more memory than our typical desktop systems have. While desktops typically have 8 to 16 gigabytes, our servers may also typically have 16 to 64 gigabytes, depending on the application that they're running or the service that they are offering. But they're capable of having several terabytes of memory at their disposal. Now, another big advantage is going to be the speed that memory is going to work at in the server as opposed to the desktop. And this is one area where the desktop has better performance per se than the server world. And the reason for that is in the desktop world, utmost stability is not the primary factor. Desktops are trying to reach the limits of performance, and as such, they have memory modules that operate at higher frequencies or higher I/O than standard memory is supposed to be run at. For example, DDR4 was originally designed with a clock speed of 2133 megahertz. However, it's not uncommon to find desktops configured with DDR4 3200 megahertz. While those systems are often stable at that speed, it's stressing the components beyond what a server, which relies on the stability of those components to guarantee 24/7 uptime, is willing to risk. Similarly, in the desktop world, we can overclock memory. Even if we get DDR4 3200, we can make it run at 3600 speeds or higher if we want to, sacrificing stability, increasing voltage, producing more heat, etc. in order to make that system run, but it's an option. In the server world, we can't overclock memory. And we certainly shouldn't, because it adds in an inherent instability which is completely contradictory to the purpose of that server being stability. So when we talk about memory in server systems, the memory modules will typically follow the speeds that are advertised or designed as far as the frontside bus is concerned of that particular CPU. In this case, most CPUs today are going to use DDR4 2066, 2933, or in the case of the latest and greatest server CPUs, DDR4 3200. Older CPUs might use DDR3 1333 or DDR3 1600, but realize that whatever the speed advertised for the CPU is, that's the speed of memory that should be used with that particular CPU. With a larger number of slots at our disposal, it becomes rather confusing as to what we should prioritize when we're planning memory for a server. With 18 to 24 slots at our disposal, how many DIMMs should we populate our server with? Considering the fact that we have multiple sockets, where do we put that memory? Do we put it all on one CPU or the other? Well, in the case of servers, a good rule of thumb is to try and maximize the number of memory channels that are in use. Much like in a desktop system, it's wise to install DIMMs in pairs in order to take advantage of dual channel or quad channel technologies. In servers, we want to increase the available bandwidth between memory and CPU. So maximizing the number of channels in a server system is a good idea. But we do want to keep in mind that we want to balance memory between CPUs. realize that a process may spawn on either of our physical CPUs, and if there's not enough memory on that particular CPU, the memory will be allocated in the bank that's attached to the other CPU. And while there is an interconnect between the CPUs to allow that to function correctly, there's an increased amount of latency for that data to get from one memory bank over to the other CPU that will significantly reduce the performance of our system. So maximize channels while keeping in mind that we want to balance memory across CPUs. Now, as a caveat to that, if you have a specific scenario where you want more memory on a particular CPU, you can do that. As an example, let's say that we have a virtual host and we have a virtual machine that only needs 16 gigabytes of memory, but we want a very high core count, perhaps because it's running a process that is CPU dependent but not memory heavy. It would make sense then to put more of the memory that's not going to be used on the other CPU and associate that virtual machine with the CPU and memory that are more limited so that that virtual machine has the resources that it needs and more of the resources of the system are available to the other virtual machines or other processes that we have running on that particular server. Considering the fact that servers are all about guaranteed uptime, 100% reliability and stability, realize that a memory error, which would cause a blue screen of death on a typical desktop computer, is completely unacceptable in the server world. Similarly, the amount of data I/O moving between CPU, memory, and disk drives is going to be substantially increased over your typical desktop system. What this means is that servers rely heavily on accuracy within those memory modules. And as such, they use a technology called ECC, or Error Checking Correcting Code, to ensure that any errors in memory are caught and corrected before they impact the performance of the system. It's actually a very neat system where it essentially checks every bank of memory and uses a parity bit to determine whether the data is correct or not. As a simple example, the parity bit may be used to make sure that the number of ones in every row is always even. So if there's an even number of ones already, the parity bit will be set to 0. If there's an odd number of ones, the parity bit would be set to 1 so that there's an even number. It's a very simple thing then to check, to essentially count the ones in that row. And if it's off, in other words, if the parity doesn't match what it should be based on the number of ones in that row, we know that there is a data error somewhere in that row. Now, the advanced part of ECC is the ability to actually figure out what the error is and correct it before it impacts the rest of the system. ECC memory is also used in workstations for scientific computing, where the data processing could have tremendous results either in scientific or industrial applications, and the precision and accuracy of those results must be flawless. So ECC is useful both in preserving stability, but also in maintaining the integrity of data as it's stored in memory. ECC is available in some desktop systems and almost all server systems. However, it requires both an ECC-capable motherboard and CPU, as well as ECC-capable memory modules. If you get non-ECC memory and you put it in a motherboard that's ECC-capable, it simply won't use that feature. However, if you do purchase ECC memory and try and install it in a desktop computer, it will not function. This is a pitfall that many people have fallen into when they go on eBay looking for a great deal on system memory, and they find a ridiculously low price on used server memory. They buy it and try and install it in their desktop, and it never works because it's ECC memory. It has that extra piece of error checking correcting code, and the desktop doesn't know what to do with that, and so it won't actually boot. For servers, always use ECC memory. While we're on the subject of system memory, let's also take a moment to think about system storage. Now, just like a desktop computer system, when the power goes out, all of the information that's stored in system memory is volatile, therefore it is lost as soon as power is removed. And so we need some form of persistent storage, such as a hard drive. Now, in the server side, we have a significantly larger variety of storage technologies at our disposal, from where we store the data, to what kinds of mediums the data is stored on, to how it's accessed by the rest of the computer. For example, storage can be in different places on a server. In a desktop, we usually consider the storage to be the hard drives or SSDs inside that computer case. On a server, we call that direct attached storage, storage that is physically in the same chassis as the server hardware that is going to use it. However, it's not uncommon to have network attached storage or a storage area network, which means we can take hard drives, SSDs, other storage mediums out of our primary server chassis and store it somewhere else. In fact, we can design a server that is solely dedicated to interfacing storage with other servers on the network. Now, network attached storage has made its way into the desktop world in the idea of NAS boxes, a little 4-bay enclosure that uses a network interface card to connect a small external hard drive essentially to network resources. Network attached storage in the server world is similar, but oftentimes significantly higher bandwidth. And in fact, we can take that to the next level, which is a storage area network. A storage area network is a network that is solely designed for moving data from hard drive to system. There's no internet traffic, no other types of network traffic. It's just moving data from hard drive to system on that storage area network. What this means is we don't necessarily have to boot our computer off the drive that's physically in our server. We can boot our server off of information that is actually anywhere on the connected network, including different geographic locations, which is really neat and opens up a lot of opportunities for redundancy, multiple geographic locations, as well as performance improvements of having very large disk drives, very large RAID arrays in an enclosure somewhere else on the network, and using high-speed network connections to access that information. So how do we get higher performance? Well, in the desktop world, we're familiar with high-performance drives like M.2 PCI Express drives. We're also familiar with things like RAID, RAID 0, RAID 1, RAID 5, RAID 10. We're going to talk about storage in another unit in greater detail, but realize that in the server world, we have all of those technologies at our disposal, but we can oftentimes use them to an even higher level than we can on the desktop world. For example, most desktops have a maximum of 6 to 8 SATA ports, which means that a RAID array in a desktop is going to be limited to 6 to 8 drives. However, with RAID cards or SAS expanders or expanders that allow us to connect more hard drives, our servers can actually have 24, 36, 48, or even 64 hard drives in a single RAID array. Imagine the difference of an 8-drive RAID 0 array and a 64-drive RAID 0 array. Significantly higher performance is possible, as well as significantly higher redundancy, protection from failure in those RAID arrays. Performance is also different. In the desktop world, RAID is usually performed by the CPU or some low-power chip. However, in the server world, we have RAID cards with dedicated CPUs, dedicated memory built into the card in order to control those RAID arrays and accelerate the speed at which data is written and read. Now, I'm getting ahead of myself, and I'm going to save more of this conversation for our storage unit, but I wanted to give you a little bit of a taste of the fact that our storage hardware differs slightly in the amount of performance and redundancy that we can get on the server side. But the technology is very similar. We still use hard drives, we still use SSDs. A technology that's available in the desktop world but is rarely used is the idea of hot swappable hard drives. When we switched from IDE hard drive connections to SATA connections, one of the big advantages was we could hot plug hard drives, meaning that we could unplug power and data, plug it back in while the computer was running, and it wouldn't hurt anything. In the server world, this becomes an essential feature, especially when we have large RAID arrays. If we have a disk drive fail, we need to be able to remove that drive and plug in another drive without powering down the system. So the feature of SATA to be able to hot plug or hot swap hard drives is incredibly important. This is also why most server chassis that are rack mount chassis will have all of their hard drives mounted across the front so they can easily be removed and inserted. We'll talk more about the interfaces and the performance of server hard drives as opposed to desktop hard drives in Unit 4.